Hello everybody and welcome to today's lesson on inverses and graphing logs. Today our objectives will be we will verify that logarithmic and exponential functions are inverses, and we will graph logarithmic functions using a transformational approach. So it follows from the definition of a logarithm that y is equal to the log base b of x and y is equal to b to the power of x are inverses. Remember when we talked about inverses, how do we find the inverse of a function? We switch x and y and then solve for y. And we are going to do this now with our logarithmic function here to prove that they are indeed inverses. So I'm going to switch the y and the x in our logarithmic function to get x is equal to the log base b of y. And now I'm going to use our cyclical pattern to rewrite this. Remember, this is the base b to the power of x is equal to y. So b to the power of x is equal to y. And lo and behold, that is exactly this. So that proves that logarithmic functions and exponential functions are indeed inverses. So let's practice finding inverse functions of logarithmic and exponential functions, and at the same time practice using our cyclical pattern to rewrite those functions from exponential form into logarithmic form and backwards. So in our first example here, y is equal to log base 2 of x minus 4 plus 2. I'm going to again switch the x and the y. And in order to now use that cyclical pattern to rewrite the expression, I have to isolate the logarithmic term here. In other words, I'm going to subtract 2 on both sides to get x minus 2 is equal to log base 2 of y minus 4. And now 2 to the power of x minus 2 is equal to y minus 4 is our pattern, and that's exactly what we get. 2 to the power of x minus 2 is equal to y minus 4. And we want to solve for y, right? So add 4 on both sides. We get 2 to the power of x minus 2 plus 4 is equal to y. And here is our inverse function. We can of course do this the other way around as well. X is equal to e to the power of y plus 4 plus 1. And in the same manner, we have to isolate our exponential term. So first I'm subtracting 1. X minus 1 is equal to e to the power of y plus 4. And our e is the base of a function with this exponent, and this is our result. So the log base e of x minus 1 is equal to y plus 4. Now log base e we have already discussed. That is our natural logarithm, and we also, and more commonly, abbreviate this by just writing ln. ln of x minus 1 is equal to y plus 4. We're going to solve for y, so subtract 4 in the last step. ln of x minus 1 minus 4 is equal to y. And there is our inverse function. On to our next few examples. Switching x and y, we get x is equal to 1/3 the natural logarithm of 2y minus 1. In order to isolate a logarithmic term, first we're going to add 1 to both sides. And in our next step, we're going to multiply both sides by 3. which cancels out here, and on the left I'm going to distribute. To rewrite this in exponential form, we now need our base. So what I'm going to do is I'm just going to rewrite this showing our base, because our natural logarithm is the logarithm base e of 2y. And now we are ready for our cyclical pattern. It's going to be the base to this power is equal to that. E to the power of 3x plus 3 is equal to 2y. And last step, divide both sides by 2. E to the power of 3x plus 3 divided by 2 is equal to y. Nice circle around it, and there is our inverse function. Last but not least, over to the other side, x, and we remember that f of x is just another way of writing y. But instead of writing that y, I'm going to write x is equal to 2 times 3 to the power of y minus 2 plus 4. First, subtract the 4. Then we are going to divide by 2. And I'm actually going to write this and distribute the fraction. So I get 1/2 x minus 2 is equal to 3 to the power of y minus 2. And ready for our cyclical pattern. The log with base this of this is equal to that. Log base 3 of 1/2 x minus 2 is equal to y minus 2. And in our last step, add the 2 on both sides. Log base 3 of 1/2 x minus 2 plus 2 is equal to y. And done. Next, let's talk about how do we graph logarithmic functions. Using our transformational approach with our parameters a, h, and k, and now we're also adding b as the base of one of the new one, we can translate the parent function f of x is equal to log base b of x. And the way we graph it is we have a vertical asymptote. Remember, the logarithmic function is the inverse of the exponential function. The exponential function had a horizontal asymptote, and as we reflect this function across the line y is equal to x, we now end up with the vertical asymptote. Then we create a convenient table of values for the parent function, and those values we then translate point for point using a, h, and k. Why do we have a vertical asymptote? The other reason for that is that, remember we said we can never have a logarithm of 0, and so x can never be a number that's going to make this part of the expression 0. Therefore, h is that number that we can never reach. So let's remember the table of values that we have used for our exponential function. When x was -1, 0, and 1, y would be 1 over b, 1 or b. These are key values for the exponential function. And since the logarithmic function is the inverse of an exponential function, we just flip the x's and the y's. So the y's are now our values -1, 0, and 1, and the x's are 1 over b, 1, and b. So these are key values that we're going to use to graph our function. And of course, they're going to be different depending on which number is the base of our specific function. So in our example here, y is equal to the log base 3 of x plus 2 plus 1. So let's find our a, b, h, and k. A is 1. B, the base, is 3. H is negative 2. And k is 1. Let's create our table of values. X will now then be 1/3 if our base is 3, 1 and 3. And y will still be negative 1, 0, and 1 if we did not have an h and a k. So that means if we didn't have to translate or dilate our points, we would plot them like this: 1/3, negative 1, 1, 0, and 3, 1. But now we have to translate those points. We have to move them 2 steps to the left for h and 1 step up for k. So 2 steps to the left, 1 up. 2 steps to the left, 1 up. 2 steps to the left, and 1 up. And that gives us our logarithmic function. And that also shows us where our asymptote, our vertical asymptote, will be. And as we had said, the vertical asymptote is at the value of h. In this case, it is at x is equal to negative 2. It's also way easier now to find our domain and our range. The domain starts at negative 2, but it actually never touches negative 2. So we need our open parentheses, negative 2, and goes all the way to infinity. Our range, however, is unrestricted and goes from negative infinity to positive infinity. Very good. So now let's go do a couple more examples like that. Y is equal to log base 1/2 of x plus 3 minus 2. Let's find our a, b, h, and k. A is again 1. B is 1/2. H is negative 3. And k is negative 2. Our h also gives us our vertical asymptote. So let's write that down right away, because that is helpful for our graphing effort. Also, x is equal to negative 3. And now let's get our values before translation. X and y is equal to 1 over b if our base is 1/2. 1 divided by 1/2, make it the reciprocal, we get 2. And the next value is 1. And then b itself is 1/2. And our y's are again untranslated, are negative 1, 0, and 1. Let's graph our asymptote at negative 3. And our points before translation would be 2, negative 1, 1, 0, and 1/2, 1. And now we have to move those 3 steps to the left and 2 steps down. So 1, 2, 3 to the left, 2 down. 1, 2, 3 to the left, 2 down. 1, 2, 3 to the left, and 2 down. And here goes our logarithmic function. Our domain is negative 3, not included, all the way to positive infinity. And our range is negative infinity to positive infinity. On to our last example. Y is equal to 2 logs base 2 of x minus 3 plus 1. So now we finally have an a that is not 1. It is 2 in this case. B is also 2. H positive 3. And k positive 1. Our vertical asymptote is at x is equal to positive 3. Table of values, x has to be 1 divided by the base, so 1/2, 1, and the base itself, while y is -1, 0, and 1. Our vertical asymptote is at positive 3. And so since we have a dilation of 2, now our y values need to get multiplied by 2 each time to give us our new values, and that would be -2, 0, and 2. So before we translate those values, they would actually be at 1/2 and -2, 1 and 0, 2 and positive 2. But translated 3 steps to the right and 1 step up would be 1, 2, 3 to the right and 1 up, 1, 2, 3 to the right and 1 up, 1, 2, 3 to the right and 1 up again. And here goes the graph of our function. Our domain goes from positive 3, not including, to infinity, and our range goes from -infinity to positive infinity. Alright, you guys, so much for this, and I will see you in class.